So the next part of this section, we're going to talk about a specific base we can use for our exponential function. So the base is the number that we are raising the power to. So this specific base is called e. This is the natural base. E stands for a number, 2.718281828, and it goes on forever, kind of like pi is a repeating decimal that goes on forever. Same thing with e. So the natural exponential function, we call it, is f of x equals e to the x. So it's just saying we have a base of 2.718 and so on. And this is going to have special functions as you see as we get into logs and all of that stuff that goes along with exponential functions. So it follows all the basic characteristics of exponential functions, as you can see from the graph on the right. When e has a positive exponent or a positive x, from right or left to right, it goes up. And then when it has a negative x, from left to right, it goes down. So where does this number come from? We can use the expression 1 plus 1 over x to the x to approximate that number, 2.718. And we can actually see that when we graph out this function. So as you can see, I have graphed that over here on Desmos. And we have this line that curves and it's going to be approaching some number, which is actually the number of e. So as you can see over here on the left, this line right here is 2.5 and this line is 2.3. So if we follow this, you see that this is starting to approach a number between 2.5 and 3, which is that number, the 2.78 number, which gives us the value of E. So this does approach an asymptote, and the asymptote is the value of E. All right, so moving on. So we can use our calculator to evaluate the natural exponent. On the calculator, you will find that button for E. If you press second ln, so second is the blue button up top left, and then ln is right to the left of 4. That gives you e to a power. If you just want the regular e button without raising it to an exponent, you can press second division sign, and that also gives you e. So second ln is the one we typically use because usually we're evaluating e to some power. So we can do a couple examples here. So x equals -2. If we plug that into the calculator, we're going to say e to the -2 equals what? Because we're evaluating e to the x. So that would be second ln, and then we would type in parentheses, -2, close the parentheses, and you should get 0.135, and it'll go on multiple decimal places, but we can round to 3. Our next one, so we have x equals 0.25. So for e to the x, second ln, parenthesis, 0.25, close the parenthesis, press enter, and you should get 1.28. And our last one, -0.4. So second ln, parenthesis, -0.4, close the parentheses, press enter, e to the -0.4 equals 0.67. So most of the time you'll get a decimal. You can round the decimal to 2, 3 places, or as you see fit. Going along with e, and exponential functions is compounding interest. So compounding interest is interest calculated on an initial principal or an initial amount of money, and also accumulated interest of the previous period. So um, let's say you have money in a bank or you take out a student loan and there's interest on that. You have your initial principal of what you took out. So, what was your loan on your car? What was that initial amount? And then over time, it's going to gain interest. So, compounding interest means that once it gains interest, you are now going to be paying interest on the interest that it gained. So, these formulas go for n compoundings per year. So, a compounding means how many times um, a year is your interest being added to the principal. So here we get this formula, A equals P times 1 plus R over N to the NT. So all of these letters have a specific meaning. So P is the principal, the initial amount. R is the rate at which the interest is being calculated. So maybe it's a 2% rate every year. You're charged 2%. So typically rate will always be a percent. Time in years, so this is the amount of time it's going to take you to pay off your loan, or maybe the amount of time that you want your interest to accrue. So sometimes if you put money into a bank, um, since you are letting the money or letting the bank use your money, if you leave it in an account for a certain period of time, you will actually gain interest on that. Um, so how many years are you going to leave it in the account before you take it out? And then N is the number of compounding. So how many times of year is the interest added into your account? There's something else called continuous compounding, which we're going to talk about in a moment. But first, so number of compoundings, if it's annually, that would be once a year, semi-annually be twice a year, and quarterly would be 4 times a year. So it's all compoundings for this formula are based off of a year. So how many times in a year? If it was weekly, you would do how many weeks are in a year. If it was daily, you would do how many days are in a year um, as your end value. And then we have something called continuous compounding. So, continuous compounding is where the minute you are charged the interest, it goes right into your account, and then you gain more money based on that, or you have to pay back more money based on that. So here is just kind of a little cycle that shows you. So you have $1,000. Let's say it's a 10% interest rate. So in a year you earn 100. So now you have $1,100 and you're earning 10% on that. So now you're earning $110. So this is where that compounding comes into place. Each time you are gaining a little bit more interest. So here's an example of compounding interest. It says a total of $9,000 is invested at an annual interest rate of 2.5%, compounded annually. Find the balance after 5 years. So the first thing we want to do is figure out what compound interest formula we are going to use. Since it doesn't say anything about compounding continuously, it says compounding annually. That means we're using this formula. So the only time we use the what I like to call PERT formula that uses E is if you see continuous compounding or compounded continuously. We have compounded annually, so this is the formula we will use. So the P in this equation is 9,000. That's our principal. That is the amount we are starting with. The rate is 2.5%. So 2.5% as a decimal is 0.025. So we do need to change the percent to a decimal. N is the number of compoundings per year. This says compounded annually. So this would be once per year. And T is the number of time. So find the balance after 5 years. That is our total number of time, which is 5. So now we plug all of this information into our formula, as you can see here. The next step is we are going to simplify the fraction in parentheses. Now, you can plug this entire equation right into your calculator if you want, but sometimes with parentheses and whatnot, it gets a little bit confusing, so I like to do it piece by piece. Next, we're going to combine what's in parentheses, the 1 plus 0.025, and we're also going to multiply the exponent. Next step, we are going to put 1.025 to the 5th power, because only that part of the equation is going to the 5th power, not the whole 9,000. And then the last step is multiply the 9,000 by the decimal that you get. And so you get approximately $10,182.62. So this is what you ended up with. So you started with 9,000 and now you have $10,182.67. Here we have another problem. So a total of 12,000 is invested at an annual interest rate of 3%. Find the balance after 4 years if the interest is compounded A quarterly and B continuously. So since one of mine is using quarterly and one is using continuous, I have both formulas for us right here. So once again, we're going to list out our different um, values. So our principal here is 12,000. Our rate is 3%, which I changed to a decimal, 0.03. Time is 4 years. and each of our n's are going to be different for A and B. So for A, n is 4 times per year because it is quarterly. So here I use this formula since we are compounding quarterly, and I plug in the info. Just like I did before, I'm going to divide the fraction first, and then I'm going to add together what's in parentheses as well as multiply the exponent. Next, I am going to raise that what's in parentheses to the power of 16, and then I multiply, I get $13,523.91. For compound continuous, we don't have an n because it is continuous, so it's just continually going. And we use A equals PE to the RT. So keep in mind, E is a number, so we don't have to plug in anything for that when we plug in our info. The first thing I'm going to do is multiply the exponents, and then I can just plug it right into my calculator. I get $13,529.96. So as you can see, putting in a principal of $12,000, if you compound it quarterly versus continuously, you do end up with a little bit more money when you compound it continuously because you are compounding it a few more times.